Okay, so we're going to look at a different type of sequence here. It's called a geometric sequence. So a geometric sequence kind of differs from some of the other ones like arithmetic or quadratic that we would have done, because those ones there are more to do with adding on common values or common constant kind of differences each time. Whereas what we're looking here is a common ratio. So in this case, what we're saying really is that our sequence is increasing based on some sort of multiplication of some common term at all times. So a fixed non-zero real number. So it has to be a constant term, it has to be a common term across my different terms of my sequences here. So to test whether a sequence is geometric, we simply take a number or a kind of term in my sequence and divide it by the previous term. And what we want to show is that for any number that we pick, we get the same result. So if I pick t4 over t3, that's the same as t2 over t1. They don't even have to be consecutive. That ratio should be common across my sequence altogether. And what that leads us to then is this general term of Tn, which is a or to the power of n minus 1, where a is my first term and or is my common ratio. So looking at how to apply that then, for this sequence I want to find Tn, so let's just start by filling out my formula here. I'm going to identify those terms. So a is my first term, which is a half, or is my ratio, so I take any term and I divide it by the previous term. That gives me 2 over 6, which is a third. So in this sequence, what's happening is we're multiplying by a third to find the next term in the sequence. So we're increasing by kind of increasing powers of a third each time. So to find t to the power of 7, which is the first one that I have to find, I'm just going to fill in 7 for n, and then I can input that then into my calculator here. So let's go with that. A third to the power of 6, which is 1 over 1458, leaving that as a fraction, I suppose, in this case, because all the terms seem to be fractions. The second part asks me to find the number of terms in this sequence, and focusing, I suppose, particularly on the last term. So we're given a certain kind of length of a sequence where 1 over 39366 is the last term. So really what they're saying is that is Tn. What is n? So what is the value of n? So I'm going to use my general formula here that I have, if this works for me. This decides to work. Okay. Okay, the second part of the question then, I'm looking for t, the number of terms in my sequence, given that this 1 over 39366 is kind of a particular term or particular length of my sequence. So what I'm really being asked to do here is I'm asked to find the value of n for a given term, which is Tn. So Tn is my term where n is unknown. So I'm going to use my sequence that I have, so a half times a third to the power of n minus 1 equals 1 over 39366. Multiplying both sides there, I suppose, by 2 to see if that reduces my answer a little bit here, and it does indeed. At this point, I could either take the log of both sides or go straight to log notation. So in this case, we might just go straight to log notation. So we can type in then log of a third, sorry, that's half, a third, 1 over 19683, that's going to be 9. So 9 equals n minus 1, which means n is 10. So there are 10 terms in that sequence there. Okay. One thing to note, I suppose, with this sort of geometric sequence is that we can write consecutive terms in this form, a over or, a and a or, where if we consider any term here, the previous term comes from me dividing by that ratio, the next term comes from me multiplying by that ratio again. And where that can be useful then is if we're asked about the product of some consecutive terms, because we can make use of that to show the product of 3 consecutive terms is the cube of the middle term, or a to the power of 3 there. So let's just look at another question, kind of making use of or exploiting these geometric sequences here. We're given 3 terms and we're asked to find a possible value of x. Now the main thing we know about a geometric sequence is that it has a common ratio, and that's what we're going to have to use here. So if I take any term, such as 8x minus 4, and divide it by the previous term, which is x plus 2, that should be the same as me taking any other term, so 13x plus 10, and dividing it by its previous term. So 8x minus 4 squared equals 13x plus 10 by x plus 2. So let's see, 64x squared minus 64x plus 16 equals 13x squared plus 26x plus 10x plus 20. So 51x squared minus, okay, let's just see what this gives us here. So 51x squared minus 100x minus 4 equals 0. Okay, so at that point then I would plug that into my quadratic formula to get my answer right, and I get my two answers for x of 2 and minus 2 over 51. Now in this case I was told that I want to find the two possible values of x, which I've done, and find the first three terms if x is an element of n, which means I'm finding the first three terms if x is 2. So that's going to be 2 plus 2, 8 times 2 minus 4, and 13 times 2 plus 10. So that's going to be 4, 12, and 26 plus 10, 36. Okay, 4, 12, and 36 with a common ratio there of 3. Common ratio of 3. The product of the first three terms in a geometric sequence is 216 and the sum is 26. Find the three terms. Well, this is where we maybe make use of the fact that if I pick any term, a middle term here, the previous term comes from me dividing by my ratio, and the next term would come from me multiplying by my ratio. And if I was to multiply each of those, I would just end up with a cubed. So a cubed is 216, which means a is, let's take the cubed root of 216. So cubed root of 216 is 6. So a is 6 here. Okay, the sum is 26. So let's add them up together. Plus a or equals 26. Now I could sub in my 6 here as well. So 6 over or plus 6 or equals 26. Let's multiply across by or. So 6 or squared plus 26 or as well. So 6 or squared minus 20 or plus 6 equals 0. Okay, factorizing that and solving my quadratic there gives me or equals a third and or equals 3. I'm told that or is less than 1, which means that or has to be a third, and I'm asked to find the three terms. My middle term I already know is 6. My term before that is going to be 18, and the term after that is going to be 2. Okay, let's get into some of the exam questions then in this. So the first three terms of a geometric sequence are x squared, 5x minus 8, and x plus 8, where x is an element of or. Use the common ratio to show that x cubed minus 17x squared plus 80x minus 64 equals 0. So common ratio just means I take any term and divide it by the previous term, and that should be the same no matter which term I start with. So then following essentially the same as the example we just had, x squared by x plus 8, and all I'm really being asked to do here is to show or kind of end up with the same quadratic that they have, or cubic I should say, in the question here. 8x squared, let's bring everything over to one side, so x cubed minus 17x squared plus 80x minus 64, and that's as required. The second term of a geometric series is 21, the third term is minus 63. Find the common ratio in the first term. Well, in this case I'm given consecutive terms, so I know that t3 over t2 is going to give me my common ratio. So that's minus 63 over 21, which of course is just minus 3. So my ratio is minus 3. The first term then, to find my first term given that I know my second term, we can kind of make use of that here. So my second term, I could use my formula, a or to the power of n minus 1, and I know that the answer here should be 21. A times minus 3 to the power of 2 minus 1 equals 21. And really all that we're ending up with here is minus 3a equals 21. We're dividing that term by minus 3. So we're going back the way to get that initial term. So my first term being minus 7. So common ratio of minus 3, initial term of minus 7. One more area or place where we see this then is an exponential function. So an exponential function is one of this kind of form, y equals a to the power of x, where a is my initial value and then the smaller lowercase a is my common ratio, or sometimes called a multiplier in a geometric sequence. And an exponential function can be written in this format. So considering that each kind of, I suppose, consecutive term or consecutive kind of value in this function follows from a geometric sequence. That's kind of what we're looking at here. So a ball is dropped from a height of 40 and loses 1/5 of its height on each bounce. Determine the height of the ball after its third bounce, and after what bounce will the ball be at a height of less than 5 meters above the ground. Okay, so the ball loses 1/5 of its height on each bounce. So if it loses 1/5, it bounces back up to 4/5 of its original height. Okay, it bounces back up to 4/5 of its original height. So that's going to be my common ratio, or it starts at a height of 40. So my initial height is 40. So Tn is 40 times 4/5 to the power of n minus 1. After what bounce? So determine the height after its third bounce, so that's T3. So 40 times 4/5 to the power of 3 minus 1, which is going to give me an overall answer of 40 times 4/5 squared, which is 25.6. Okay, or excuse me, yeah, 25, or third bounce, yes. Okay, so third bounce there. And after what bounce will the ball be at a height of less than 5 meters above the ground? Okay, so less than 5 meters. So we want Tn to be less than 5. Let's consider what it would be when it's equal to 5. So we're looking at 40 times 4/5 to the power of n minus 1 being equal to 5. 4/5 power of n minus 1 equals 5/40, which of course is just 1/8, but we can leave this 5/40. I want to convert to log format. I'm just going to take this over to the side here. So log to the base 4/5 of 5/40 is going to give me n minus 1. Let's just see what that gives me overall. So log 4/5 of 5/40 is not giving me an altogether nice answer, but we'll go with it for now, which is n minus 1. So n equals 10.3188. Okay, n equals 10.3188. So in this case, I suppose if we wanted to be less than 5, considering that we're decreasing here, we need to go up to the next one. So that will be when n equals to 11. When n equals to 11, we'll be definitely sure that we're less than 5 there. Okay, we'll look at one, I suppose, long example question, or long exam question, I should say here then. So this is looking at a particular type of triangle, a Sierpinski triangle. And it's a particular, I suppose, famous type of sequence, if you like. So the sequence starts with a triangle, and then what we're doing in each step is we're removing a triangle from the center of any of these black triangles. So you can see from step 0 to step 1, we've removed a triangle from the inside, and then that creates 3 other black triangles. And in the next step, we're going to remove a triangle from the center of each of those black triangles, and so on and so forth, until, I suppose, essentially you've nearly removed all of the black triangles from the sequence here. Now the important thing for us to note here really is that it starts at step 0. So when we have only just one full black triangle, that's considered step 0. So that's going to impact on our kind of completion of this question here. But let's kind of have a look and see, can we make some headway with filling out this table here. So at step 0, number of black triangles is 1, fraction of the original triangle remaining is also 1. In step 1 then, the number of black triangles is 3, the fraction of the original triangle remaining is 3/4. Now they're telling me here from step 1 to step 2, I go to 9/6. I can kind of spot that already as being a multiplication of 3/4. Okay, so I'm suggesting here that there's 3/4 of the triangle being removed in each case, which does kind of make sense. For each black triangle, we are removing 1 section of that, or 1/4 of that triangle. So 3/4 is being left behind or remaining there. So in each case, we're kind of leaving behind 3/4 of my triangle. So in step 2, we can even count how many black there are. So 1, 2, 3, 4, 5, 6, 7, 8, 9. So 9 black triangles and 9/16 remaining. In step 3, if we were to count them up, we get 27 black triangles, and there's 27 out of 64 remaining. So that is another multiplication of 3/4. Okay, so ideally with these sort of table ones, if you can kind of spot the pattern that's happening here, it's going to save you a little bit of counting, if nothing else. So looking then at part B, write an expression in terms of n for the number of black triangles in step n of the pattern. Okay, so we're looking for an expression for the number of black triangles. So I can see here what's happening. It looks to me like we're multiplying. We're going in multiples of 3. I'm looking for step 1, which is 3. So remembering we started at step 0, but step 1, t1 is a is equal to 3. My ratio is 3, so tn is 3 times 3 to the power of n minus 1, which I can actually use my indice rules to just reduce to 3 to the power of n, which gives us that nice result of step 0 being 1, step 1 being 3, and it's just multiples of 3, or powers of 3 if you like. Step K is the first step of the pattern in which the number of black triangles exceeds 1,000 million, which is 1 by 10 to the power of 9. Find the value of K. So let's find Tn, for which we get 1 by 10 to the power of 9. Let's try and find out what that value of n is, and then we'll know what value of n we have to get to go past that. So taking my formula from before, 3 to the power of n is 1 by 10 to the power of 9. Let's do log to the base 3 of 1 by 10 to the power of 9, giving me n, which means n is equal to, let's work that one out. So log base 3 of 1 by 10 to the power of 9, and I'm getting 18.863. Okay, so what that's kind of telling me is that 1 by 10 to the power of 9 is not an exact result in my sequence, because I can't get a whole number value of n. So it's not a value in my sequence, and it's also telling me that that value is actually between the 18th, so t18, and t19. So somewhere along here, I actually reached, and I suppose closer to 19 technically, so somewhere maybe like here, I actually reached that value of 1 by 10 to the power of 9. So the first value in my term that is going to exceed that pattern will be t19 then, because we only reached it along the way, so I need to go up to t19. So my answer is term 19. Okay, so k equals 19. Part C, then step H is the first step in the pattern in which the fraction of the original triangle remaining is less than 1/100th of the original triangle. Find the value of H. So same kind of idea here again. We need to set up a new pattern for ourselves. So again, A is the first term. It's the fraction of the original triangle remaining in step 1, which is 3/4. Or is my common ratio, which is also happens to be 3/4. So Tn is 3/4 times 3/4 to the power of n minus 1, which is just 3/4 to the power of n. Okay, it's kind of the same idea as we did with the last one. Let's find the value of n, which gives me 1/100. We're not really thinking that it might be an actual value in my sequence here. More than likely won't be. And then we're going to make use of that then to give me my overall result here. So 1/100 gives me 16.0078, and that is kind of telling me that to exceed or to be less than 1/100, because we're reducing here by 3/4 each time, I'm going to have to go up to the next term, which means H is going to be 17. So 16, after 16, just over 16, I've reached 1/100, so I need to go on to 17 to say that I've definitely exceeded that value. What fraction of the original triangle remains after an infinite number of steps in the pattern? So infinite number of steps in the pattern here is immediately screaming out to me limit. So if I keep going with all my terms, okay, so if I continue my sequence forever, how much of that fraction or how much of that triangle will be remaining? So we're really taking a limit here for Tn from the previous part. I'm looking at what's the kind of, if I continue forever, what's the end result of my sequence? What value am I getting towards? This is kind of what we said at the start. If I keep reducing or taking fractions of my triangle, how much am I even going to be left with? So that's going to be the limit as n goes to infinity of, what was my term? 3 over 4 to the power of n. And what we need to do here is we need to kind of think about how our limits work. So if I take the limit of a fraction as n increases, okay, because this is less than 0, as n gets bigger, that fraction is going to get smaller and smaller. And we can even just look at it really quickly on our calculator here. So say we try different powers. If I try a power of 1, obviously I just get 3 over 4. Then I get 9 over 16. If we look at the decimals here, it makes it easier to see. 0.56, 0.42, 0.316, 0.237. So we can see as I make my powers bigger and bigger, and if we get into bigger numbers, we end up with something smaller and smaller and smaller overall. So as n gets bigger, what's going to happen is, so as n goes to infinity, Tn is going to just go towards 0. It's going to get so, I suppose, small there. So 3 over 4 is going to get so small that it's nearly negligible. It nearly just goes completely to 0. So that fraction is, I suppose, the fraction itself is getting smaller. The denominator is getting bigger, so the fraction overall is getting smaller. So as n gets bigger, Tn is actually getting smaller and approaching 0. So looking at kind of pulling in our limits there, and pulling in our limits for the term number. We're nearly used to these questions of seeing limits in terms of the series, but this time pulling it in for the term number instead. The side length of the triangle in step 0 is 1 unit. The table below shows the total perimeter of all the black triangles in each of the first 5 steps. Complete the table below. So we start off with a perimeter of 3. If we look then at the perimeter for the next part, each of these parts here, we can say has a side length of a half. So that's 1 half, 2 halves, 3 halves. Let me use a different color here so we can actually see it. So 1 half, 2 half, 3 half, 4 half, 5 half, 6 half, 7 half, 8 half, 9 halves. So 9 over 2. 9 over 2 here. So I can see going from here to here and here to here, they've given me a value as well. We can see, can we spot any pattern? I can kind of see we're multiplying by 3 over 2 there. So using that to fill in my other values, I get 81 over 8 and I get 243 over 16. They asked me to find the total perimeter of the black triangles in step 35. So we need to set up our Tn here, where A is my first term. In this case, making sure again we don't go for step 0. So that's 9 over 2. 3 over 2, excuse me, here, 3 over 2 to the power of n minus 1. Okay, and in this case, I'm looking to find T35. So that's 9 over 2 by 3 over 2 to the power of 35 minus 1. And I can fill that into my calculator to get me an overall answer then. So 3 over 2 to the power of 34 gives me 4, 3, 6, 8, 3, 2, 9 to the nearest unit. So quite, I suppose, in depth there. I suppose quite, I suppose, units really there, as opposed to centimeters, for example. It's just given in units. Okay, so quite big there altogether. Use your answers to parts C and D to comment on the total area and total perimeter of the black triangles in step N of the pattern. So let's focus on area first of all. So area is going to rely on the number of triangles. And we know as n goes to infinity, Tn goes to 0. So that tells me that the area will also go to 0. So obviously if we have less triangles, and if those number of triangles go towards 0, then of course the area as well is going to tend towards 0. In terms of the perimeter, we can look again at the term, I suppose, that we have here, which is 9 over 2 and then 3 over 2 to the power of n minus 1. And we can look at what happens to this sort of fraction as n approaches infinity. So if I take my limit as n approaches infinity of this term here, the 9 over 2 is nearly a constant part. It's not going to impact my limit, particularly because there's no n part to it. So really we're focusing on this part here. And we could even take out a factor of 3 over 2 there as well if we wanted to, that power of 3 over 2. And we might choose to rewrite. So I've rewritten my fraction there as in one way. We could rewrite it in another way by writing it as 3 by 3 over 2 by 3 over 2 to the power of n minus 1, which gives me 3 by 3 over 2 to the power of n, which is much easier for me to take a limit of. So the limit as n goes to infinity of 3 over 2 to the power of n. As n goes to infinity, instead of this going towards 0, because this fraction is greater than 1, what's going to happen is, as I increase those powers, the denominator is going to stay, or the numerator is going to stay bigger than the denominator. So my fraction overall is going to be top heavy. So it's going to keep getting bigger and bigger and bigger and bigger. So as n goes towards infinity, so too will this limit. The limit as n goes to infinity of 3 over 2 to the power of n, that's also going to go towards infinity. So therefore we can say the perimeter goes towards infinity. So the perimeter goes towards infinity, where the area goes towards 0. So a good question there, pulling in limits into those terms, which isn't one that we see as often as we do with the infinite series, of course, that we look at, I suppose, in the next little part here. But good to kind of pull those things together. But generally with geometric series, you're focusing on common ratio across the board there and making use and exploiting that where we can. But when you see geometric series or geometric sequence, the first thing you should think is common ratio. I take any term divided by the previous term, I get the same common constant ratio across the board.